summer school. And I have some announcements to start with. The first announcement is that Rien and Dimitris would like to ask you for feedback about the exercises, because we were iterating actually very long on designing them, and we want to improve during this week even further. And one important question is if this principle of having guided solutions, in the sense that basically there is a MATLAB file, a template where you fill in some lines, so to say, and you get a lot of contents done in a short time, but you don't write every line of code yourself, if this principle is good. And that's why they made up a feedback form that you should visit once. And so please, those that did not yet fill in the feedback form, visit this feedback form and just click and submit in order to give us this feedback. So the other important information is that you will find, of course, all the slides and very soon also the videos on the web page as well. The talks of yesterday are here, and now this morning we will have first a talk on Newton's method and second a talk on simulation methods that will be given by Rien. And then we go into the next exercise. So if there are no questions about the procedure, about the feedback form, I suggest I start. And this talk is introducing or discussing a technology that's called the Newton's method, which is used throughout this course at every little detail of numerics. So it's something very fundamental that we should know about, which is used in optimization, which is used in simulation, and it's used in many fields of numerics. So we should really be familiar with what the Newton method does and when does it converge and why. So let us start. The talk is structured as follows. I will first introduce the plain Newton method, then introduce the general class of Newton type methods, which are much more general, discuss, actually even prove the convergence result that exists for these type of methods, mention the topic of globalization, because Newton's method usually doesn't converge like that, and show how this can be directly applied to unconstrained optimization, which is what we will do in the next exercise. Okay, so what does Newton's method do? It's regarding a nonlinear root finding problem, and I call the function that we want to bring to zero big F, and the variable I call W. W is a vector consisting of n elements, and it might later be the variables of an optimization problem. It might later be the variables and the Lagrange multipliers of an optimization problem, but it could also be the variables of an implicit integration scheme that Rien will introduce. So root finding problems are everywhere in numerics, and so that's why we keep it general in this talk and not specialized yet. So this is the task. N is the dimension of W, but also the dimension of F. So you have exactly as many equations as you have unknowns, so that it's a square system, as we call it. Actually, square is the Jacobian of F. And so there is a chance that this system is well defined and leads to a unique solution, and at least locally we can identify when these solutions are unique. And so now the question is just to get it. How do we compute it? If you don't want to use a computer algebra systems, maybe because your function f is a very long and complicated expression, or for any other reason, you cannot use a computer algebra system, which is also maybe possibly very expensive. So Newton's idea was to just start with an initial guess, something that is approximately making this zero, and then recursively generate a sequence of iterates, wk, that you get by linearizing the nonlinear equation. So you look at this equation, you linearize it at some point. You need to decide at which point you linearize, because it's a nonlinear equation. It makes a difference where you linearize it, but this is the first order Taylor series, and you say this should be zero. And by setting this thing to zero, you create a linear equation system, and the beautiful thing is that linear equation systems are things we can easily solve. So that's, of course, the underlying fact that the Newton's method relies on. It relies on linear algebra for solving linear systems. And then you can explicitly compute the next iterate by this expression, which is not actually how you would implement it. So there is a matrix inverse here. You would usually not compute this matrix inverse first and then multiply it with this residual vector f. We call this f the residual, but usually you use, for example, in MATLAB the backslash operator, which is numerically more efficient. So you actually will have a factorization of this matrix instead of its inverse. But one remark I should already make here is that you have to assume that the Jacobian matrix, which is a square matrix, that this matrix is invertible. And sometimes it is not the case, and then Newton's method gets problems. Okay, but now this is the basic idea. I think it's easy to remember. I usually remember this step from here to here, and then the rest is just reformulation. So this is an easy way to remember the Newton's method. Linearize what you cannot solve directly. The philosophy is really, really easy. So I want to give you one example, a one-dimensional example, so that's easy to compute. The fifth root of 2. Yeah? So how would we compute the fifth root of 2? Actually, we would just formulate a root finding equation that says w to the power of 5 minus 2 should be 0. Yeah? And then you can compute the derivative. What is its derivative? It is 5 times w to the power of 4. For most values of w, this is even a positive number, so it's invertible, so that's nice. And then we formulate the Newton iteration, and we have here this inverse, here the residual, and we can go on. And if you start this, you can try that. Very quickly you will converge to the solution, w star, which is making this f0. And there is an interesting fact about Newton's method. It converges what we call quadratically. So let me define briefly what these convergence rates mean and what they are. So quadratic is from all the ones, the convergence rates that we encounter in practice with iterative methods. It's already the thing that is like the best thing that we usually encounter. And there exist some other rates that we also encounter quite often, which I all want to define. So a sequence wk, so just some sequence in a suitable space, converges to a limit point w star. And we assume that it converges already. So that's the first assumption. And then we can define the rate of convergence. And the rate of convergence is called q linear if there exists some scalar number alpha, which should be smaller than 1, which we call also the contraction rate, such that and some k0, because we don't care about the first iterates, so that all iterates that come after k0 have this property that they come closer and closer to your limit point w star by a linear contraction. So if this is small and alpha is smaller than 1, then this will be even smaller, and the rate of convergence here is called linear. So it's actually a geometric decay if you think so. So it's exponentially decaying if you have linear convergence. So that's a slow convergence rate in practice depending on alpha. But if alpha is 0.01, for example, like 1%, then you would call it even fast, right? I mean, then you get 2 digits in every, I mean, if it's dividing, if alpha is actually so small that it's just 1%, then you will get in every iteration 2 more digits which are correct, for example. So it can be fast, it can be slow. If alpha is just 0.99, so very close to 1, you will nearly make no progress and you will take ages until you converge. So it depends very much on this alpha. And if you have a good contraction rate, let's say something between below 1/2 or even below 1/10, then usually you are happy. But if not, you can be very unhappy with q-linear convergence. So the next good thing to have is superlinear convergence. And this is something where the contraction rate itself converges to 0. So this is like nice because the alpha, even if it was bad and big at the beginning, it will get close to 0 and arbitrarily fast later. And so you get what you have to satisfy this equation, alpha k, this contraction rate gets shrinking and better. So you eventually get good convergence. And even better and nicer, so to say, is quadratic convergence. What is this property that Newton's method has? And we introduce another constant which has different units, so I call it beta now. And there should exist a beta and some iteration index k0, such that for all k which are bigger than this zero, this k0, you would have a contraction equation which says that your next iterate should be closer to the point than beta times the square of the distance of the previous point. And so this square is what makes the big difference here, because it means that if you are already small, let's say 10 to the minus 2, after you square it, you get 10 to the minus 4. And if you square that again, you get 10 to the minus 8. And you see, incredibly fast, you can approach zero error. And that's what Newton's method does. So you get the correct digits. So the number of correct digits in your solution, if you want to, for example, solve this fifth root of 2 problem, the correct digits double in each iteration, and that means that once you have already a decent solution where you have 2 correct digits, for example, you only do one more iteration, you get 4, you do another one, you get 8, and you do another one, you get 16 digits, and then your computer actually gives up and cannot be more accurate anyway. So you basically have the best possible solution that your computer can deliver after a few iterations. And let's say in a practical rule of thumb, you would say if you have quadratic convergence and you are already in the area of convergence, 6 iterations and you have your solution up to machine precision. So you cannot do any better. So Newton's method usually takes 6 iterations if it converges quadratically. That's a very funny number. And of course, it's just a rule of thumb. So these are convergence rates, and Q quadratic, as I said, is the dream thing, and Newton's method has this property. But there are Newton-type methods which might have slightly slower convergence rates, but might be cheaper per iteration or more doable. And so in a more general term, you can always approximate in a Newton's method the true Jacobian, this thing, I call it now J. This is the Jacobian, df by dw, this matrix that we can invert, or that we cannot invert in some cases, but which is a square matrix, this J. We can approximate it by something we call M. And because it could be a different approximation in every iteration, I call it MK. Okay, so every iteration we choose something that could be an approximation, or that should be similar to the J, but not be identical. And then our iteration would just go like this formula here, wk plus 1 is equal to wk minus the inverse of m applied to the residual f. So please note that we can approximate this matrix, but we should never approximate the residual f. If you approximate that, you cannot even check that you're converged, right? So you need to have something that is actually not moving anymore if you are at the solution. And this has the property, so if you start in the solution, this f will be 0, this thing will also remain 0, and you stay in the solution. That's like the minimum thing you want. So never approximate the f. The residual should be evaluated correctly. You cannot do without, but you can approximate the matrix. And so now, depending on how closely this m approximates the j, the convergence rate can be fast or slow. Yeah? So this is an interesting tuning parameter. I want to just give one picture that is important maybe in this context. If you have a root finding problem in this context that we have, there is a variable w, there is the function w, f of w. And your function f of w could have, as I said, it's possibly a curved function, and you evaluate it at some point. And what the normal Newton's method does, it evaluates the function and it evaluates the tangent, and it looks for the 0 of your function with this tangent. And that's what converges quadratically, as we said. So what we now do is we evaluate the function, and because this m is not exactly the derivative, it's not exactly a tangent that we use for approximation, we actually use something else, which is not a tangent. This is the Taylor expansion, the wrong one. That's if this is wk, then this is Wf of Wk plus Mk times W minus Wk. So it's a linear function which has the property that it's the same value at the point where we evaluated it. Sorry, this is not this is Wk, and this would be 1 Newton iterate, and this would be 1 Newton type iterate. Yeah, so here's Newton, and here's Newton type. And you see already that this is, in particular when you're close to the solution, this is not such a good approximation, but you see on the other hand that if your bad derivative, I mean this approximate derivative, is not too far from the true one, that then you will still converge. And that's the beauty of these Newton type methods, that a lot of iterative schemes can be interpreted as a Newton method now. Actually, even schemes to solve linear equations, that's a beautiful thing. You could even try to solve a linear equation. The linear equation is something where you just have an affine function that you want to find a zero of. And if you, for some reason, have a bad derivative, you could still iteratively refine your solution and get an converge to the solution of your linear system. So Newton's method, or Newton type methods can even be used to interpret methods for solving linear systems. So it's a quite general setting, and I wanted to share with you one theorem which is relatively easy to prove, and so we also prove it, which gives basically a nearly complete answer to convergence of Newton type methods. It's a slightly simplified version of a more elaborate theorem that was proved by several people. What we actually want to derive is that if you start this Newton's method close enough to a solution, and it's a general proof for all Newton type methods. Yeah, so it's for this iteration with an M. So you have to start close to the solution, and there must exist two numbers, and we call them omega and kappa. And there should be two conditions satisfied, and these conditions I want to discuss. The first one is a Lipschitz condition on the Jacobian. So it's something problem specific. For just scaling reasons, we multiplied with these inverse here. But most important is that we have a difference between two Jacobians, and the difference should not be much bigger than, or it should be bounded above by the distance between the 2 points, wk and w. So for any 2 points, right? So if actually it only needs to hold for the one of the points can be chosen to be one of the iterates, but basically you can assume it for all points. So roughly speaking, you say J, the Jacobian, should be a Lipschitz function. That's what this says. And there must be some constant omega which should just be smaller than infinity. That's the only assumption we have to make. This is something that any differentiable function on a bounded domain will have, on a compact domain. So that's a nice thing, as long as your inverse matrices are bounded. But these are the things that you can choose, right? So the other thing is a compatibility condition which tells us how different our m could be from the true derivative. So that's the difference between this slope and this one. So here's m, and here is j of wk. So the distance between these two things should be not too big, and actually the measure of distance is best expressed in this form, where you take the inverse of m, multiply it with j, and subtract from it the unit matrix, actually. Yeah, so I should just write down this equation in another form that might be more... can you still see it? Yeah. So you could actually say what you want is that this mk to the minus 1 times j of wk minus the unit matrix should be small, right? So it should be something that has to do a lot with the true inverse. And of course, if you would take m to be the real Jacobian, then this kappa would be just 0, because these two things, the m and the j, would be identical. Okay? So we see that this kappa is 0 for the exact Newton method, but for the inexact Newton's method, it might be non-zero. Okay, and this contraction theorem that we have here, which I state in a form which you can find, I think, in this form in the PhD thesis of Hans-Georg Bock, who will visit us in next Thursday, so you can discuss more about this if you want. So kappa and omega are the same names that are used in his school of thought. And the contraction rate here, you see, is actually linear if there is a kappa. This term gets small if it converges, right? But the kappa will remain. So asymptotically, it would just converge with the convergence rate kappa. If the kappa is 0, like for an exact Newton's method, this and this will be multiplied and you get directly quadratic convergence. So we have actually, if we prove this theorem, then we have proven quadratic convergence for Newton's method, but we have also proven linear convergence for Newton type methods. And I should say, because I decided to simplify the notation a bit, if you would have the property that these kappas during the iterations go to 0, which would be another assumption, so actually this kappa would converge to 0, then you would get here a kappa that converges to 0, and you would even be able to cover the case of superlinear convergence, but I don't do it in this setting. So this is a nice, a clean statement of when does this thing converge. The assumptions can be tightened or loosened, so there are different formulations of it, and I chose this one because it's convenient to use in the proof. And it's also something which is, I should say one thing, what we have here is something that has, because of this inverse, it has the units of W. So it's a nice property. Whatever the units of our function f are, they are, so to say, counteracted by this inverse of m. So if you multiply, for example, your nonlinear root finding problem with a factor of 1 million, this Lipschitz condition will not be changed if you also multiply the m with 1 million. Okay, so yeah, we can prove it or we can also not prove it. Time is limited. I have 2 slides for the proof. I just want to have a look at it. Because it's relatively easy, but on the other hand, it's then getting very technical also. So the tricks when proving such a theorem is, first of all, you add something that is, you expand the wk plus 1, right? So that's easy. And then we subtract a 0 here, because f of w star is 0. So we can just subtract the 0 here, so that's nothing bad. And then we just rewrite this term here by using another unit matrix, mk times mk to the minus 1. And this mk we had here, we pull it out. But now the crucial step here is to go from fwk to fw star. We can use the mean value theorem by just integrating over the Jacobian of f. That's the crucial step here. So that's actually, this term can be expanded by integrating over the derivative along the line from w star to wk. Okay, and then we have we use we subtract from the first and from the last term. Oh, here should be a j. This is wrong. Sorry. So we subtract this j here, and we subtract the same j here. So that's a j. Sorry for this. This is a j. And so we subtract just nothing because it's here with a minus sign and here with double minus sign, so it comes with a plus sign, and the integral is from 0 to 1, so it's just integrating to 1 because it's a constant for the integral. So now you have, so to say, just added nothing to your equation, and that's always the trick. So now you have one expression here, of which you can now use our bound, and another expression here, for which you can also use our bound. And that's what we will do. So taking the norm on both sides will actually give you that the distance between the new point and the solution will be bounded by kappa times the distance. That's the first term. I jump back, so it's this term here. Yeah. So that was kappa. And then the second term, we will keep the integral, but we take now the omega, which gives us a bound on the distance between the 2 Jacobians because of this Lipschitz property. And then we need to just reorder terms and see that this is basically a this difference between wk and w star. So there's a strict equality here now, where you have to evaluate this integral, and this integral is evaluated to 1/2, and that's where this 1/2 comes from. And at the end, you have the equation that we wanted to derive. So it's quickly done, and we have proven it. And actually, you can even say something which I didn't state in the theorem. I jump back to the theorem. I say if W star, the distance to the true solution is sufficiently small, so how small should it be? It should be so small that this term here is smaller than 1 already for the first iterate. Because if it's smaller than 1 for the first iterate, the next iterate will be even closer and it will become even smaller. Okay, so that is the local contraction theorem for Newton type methods, and it's a very general and powerful tool that I wanted to share with you. So there's one practical problem with this. When you start a Newton type iteration, you don't know where the solution is, right? If we would know where this thing is, we wouldn't start it anyway. So usually when you start, you don't know if you are close or far away from the solution. And so what we need to do is what is called globalization. So you need to make sure that your Newton's method converges globally independent of where you start. And it's a bit funny, you globalize it so that it sometime enters the area of local convergence, and once you're in the area of local convergence, so the area where this theorem, so to say, applies, you converge extremely quickly to the solution. So Newton's method is wonderful, but only if you're in the local convergence area, and before you need globalization. And I just wanted to mention 3 globalization strategies which are used in practice and which are very useful. The first one is what we call a homotopy. So you modify your root finding problem to something that is either easier, for example linear, or even solved. Yeah? And like the most trivial example for a solved problem would be something where you just say, I subtract my initial guess from my f. So then the system is solved by definition, right? When I set lambda to 1, I just say this is an easy root finding problem, which depends on a parameter lambda, which we call the homotopy parameter. And then you have a solution, and you know that you're close to the solution if you change it a little bit. And then you remain in the area of convergence all the time while you slowly change the homotopy parameter. And so each time you need to restart the Newton's method at the previous solution, then you converge, then you change lambda a bit, then you converge again. And if you do both things simultaneously, you can even get a quite efficient method. That's what we will do, for example, for interior point methods. That's the strategy that we use there for globalization of a Newton's method, so to say. So now for a second approach is to do a line search. And so a line search would just say, let's make the steps small. I mean, when these steps might be too big, you see they might be somehow leading you away from the solution. So we make them smaller by some damping factor that we call alpha here. So you basically multiply your step with alpha k, and this alpha k needs to be determined by some condition that is actually usually backtracking. You make the full step, you check if some function is reduced that monitors progress, and you make it smaller and smaller. I should say that if you just look at it from this perspective, this alpha k, you could just say it's nothing else than just increasing the matrix M to M divided by alpha. Yeah, so in some sense it's if you would have, for example, a fixed step size parameter, it would just mean that you choose bigger matrices M. And the third way to globalize is based on so-called trust regions, or related to it, a Levenberg-Marquardt modification. So it's the philosophy here is that you modify the iteration in some other way, not just by taking smaller steps, but in some other way, so that the distance between two iterates remains sufficiently small. And one example could be that you add to your iteration matrix something like a unit matrix with some possibly big factor beta, And this way also you make your matrix bigger, this thing that's inverted, and that means that you make the step smaller. Yeah? And making this big enough, your step will become smaller. So this is different families, and they are of course all extremely related with each other. Yeah? So I should also say that the homotopy, this one, is closely related to the line search, because in some sense we just reduce the residual by having this lambda, and which is, if you could either increase the matrix M, or you could also interpret this as making the F smaller. So these are all different perspectives on the same thing. What you want is basically that your steps are not getting too big to bring you out of the area of convergence. Okay, so that's the big ideas of globalization in a very superficial fashion. But let's now finish this introduction into Newton's method by making the connection to unconstrained optimization, to the simplest setting that we have been familiar with already, and which we will also do in the exercise after today's talks, this morning's talks. And if you want to just solve an unconstrained optimization problem, you could just say, what I want is actually to find the root of the gradient. So we set actually the iteration variable identical to the optimization variable, so w and x are identical here, and the function f of w is the gradient of f, of the little f. So the little f is a scalar function, its gradient is a function with n components, and we want to set this gradient to 0. And then if you just see what exact Newton's method would do, you need to take the second derivative of f in order to get the Jacobian of the gradient, right? And then the exact Newton method iterates like this. You have here the inverse of what we call the Hessian matrix. It's the Hessian of the objective function. And of course you can also replace this Hessian matrix by something else. Yeah, I called it M before. Now let's make sure that we, for the case of optimization, I call it B. So BK should be an approximation of your Hessian matrix. The Hessian matrix is symmetric, so we should choose this BK also to be a symmetric matrix. But there are many possible choices. And one choice, the simplest choice, would be that you just take the BK to be a unit matrix, and that means that you just take a step in the negative gradient direction, which is called the gradient method, or also the steepest descent method. Yeah? So that's the simplest approximation. It's a Newton type method, but a very primitive one. You could do something that's called a quasi-Newton update. That is most successful or most widely used is the BFGS update. There are others. You could use something that is called the Gauss-Newton Hessian approximation, and that's only applicable if your objective function was a square function, like the square of a lot of residuals. Yeah? So big R is a function with many outputs, for example, the fit of a nonlinear fitting problem. And then the Gauss-Newton Hessian is obtained from linearizing this R and basically, throwing away some other terms of the second derivative and keeping the one that is dominant and also nicely positive definite, or positive semi-definite, this expression here. And you can use, of course, the exact Hessian. I didn't mention that, that's what we do here at the top, right? But you can also do the exact Hessian and add something to it, which is sometimes useful because you might want to ensure positive definiteness and a descent property of your iterates, so that it's going into a downhill direction. And this would be one possible modification where you take the exact Hessian, which might be positive definite or not. You add something to it, which is making it definitely positive definite. You could add something else in a unit matrix, but this is a general procedure that is very often taken. In all cases, when you modify this matrix, you will lose, usually you will lose the quadratic convergence. There are some few exceptions where you could keep quadratic convergence even though you don't work with the exact Newton method here. One example, for example, if you want to converge to a root finding problem with the Gauss-Newton method, to a least squares problem, and you know that the solution has 0 residual, then it turns out that even Gauss-Newton has quadratic convergence. Yeah, that's it. So that was a short primer in Newton's method. So I hope that you're familiar whenever you see a nonlinear root finding problem, how to solve it with Newton's method. And we will see a lot of nonlinear root finding problems in the sequel. And we will discuss some of the details of how to solve the linear and nonlinear systems later. But this is the basic algorithm we will always see again and again. And I hope by doing even the convergence proof you feel this is not magic, but just a very simple and reliable method. Thank you. Yeah, I would suggest we take no long break, just a few seconds or minutes, maybe 2 minutes. Enough to go quickly to the toilet if you want.